All right, check this out. What if you could hack a login, not with some super complex password, but just by mashing a single key on your keyboard? Sounds completely nuts, right? But today, we're going to pull back the curtain and see exactly how a simple coding mistake can turn a long string of A's into a master key.
Okay, so let's get right into it. On the left, you've got the normal, everyday scenario. Program wants a password, you type in the wrong thing, access denied. Makes sense. But then, look at the right. Something totally bizarre is happening. We just throw a ridiculously long string of A's at the program, and somehow we're in. Yeah, this isn't some secret feature. It is a huge, catastrophic flaw.
So, the big question is, how in the world is that even possible? To figure this out, we need to basically become digital detectives. We're going to investigate the scene of the crime, which in this case is the program's own memory.
All right, so our investigation starts deep inside the program's memory. We're heading to a very specific place, a kind of temporary workspace that every function uses to get its job done. This place is called the stack.
So what is the stack? Well, it's just a temporary storage spot. The easiest way to think about it is like a stack of plates, right? You add a new plate to the top, and when you need one, you grab the one from the top first. In the world of programming, this is where a function keeps all its temporary stuff, its tools, its local variables, while it's doing its thing.
You know what? Let's make that analogy even simpler. Just picture the stack as a small, tidy little desk. Whenever our password-checking function needs to run, it just lays out everything it needs to work with right there on that desk.
So the very first thing our function puts on its desk is this little marker, a variable called offFlag. By default, its value is 0, which basically means false, no access yet. You can think of this as our little gatekeeper.
Okay, so right next to that flag on our desk, the function puts down an empty box. This is our password_buffer. It's just an empty space waiting to hold whatever password the user is about to type in. So there we have it, our two key items sitting right next to each other in memory.
All right, so we've got the crime scene mapped out. This tidy little desk in the computer's memory. Now, let's talk about the weapon. The thing that causes all this chaos.
The weapon has a name. It's called buffer overflow. This is a classic vulnerability. It happens when a program tries to shove, say, a gallon of water into a tiny pint glass. That glass is our password_buffer. The program doesn't bother to check if it'll fit, it just keeps on pouring.
And that overfilled glass analogy is perfect, really. Because think about it, you pour too much water into a glass that's sitting on your desk. The extra water doesn't just vanish, right? No, it spills everywhere, and it soaks that important offFlag paper that was sitting right next to it. That spill, that's exactly what the attacker is exploiting.
Okay, time to connect the dots. We know the crime scene is the stack. We know the weapon is the buffer overflow. So let's put it all together and finally solve this crazy authentication mystery.
So here's how the whole attack plays out, step by step. First, the program sets up its desk and our little auth flag starts at 0, false. Then, in step 2, we come along and feed it that super long string of A's. Now here's where it all goes wrong. In step 3, the password buffer, that little box, fills up completely. But the program doesn't stop. It just keeps writing those A's. And that overflow leads directly to step 4, where one of those extra A's literally spills over and gets written right on top of our auth flag variable.
And if you want hard evidence, here it is, straight from a debugger. Look at the memory addresses. The password buffer's address is just a little bit before the auth flag's address. This is the smoking gun. It proves that as we keep filling up that buffer, we're marching steadily up through memory, right towards our target. This isn't random chaos. It is a direct, predictable attack.
But wait a minute, how does writing the letter A suddenly mean access granted? Well, it's because deep down, computers see letters as numbers. The ASCII code for a capital A is the number 65. Remember our auth flag? It was an integer waiting for a number, and it started at 0. So when we overflow and write an A on it, we're actually changing its value from 0 to 65. And here's the kicker. In languages like C++, any number that isn't 0 is treated as true. And boom, just like that, the gate swings wide open.
Okay, so right now you're probably thinking, aha, I know how to fix this. Just declare the variables in a different order in the code, right? Protect the flag. And you know what? That is a perfectly logical thought. But the compiler, it can throw a nasty curveball you might not see coming. So look here. On the left, we have the original, vulnerable code. And on the right, we've made what looks like a simple fix.
We just swapped the two lines. We now declare auth flag before the password buffer. In theory, that should put the flag somewhere safe, away from the overflow, right?
Which leads us to this question. I mean, if the password box is declared last, it should be on the top of the desk, so to speak. So overflowing it should just spill into empty space, not onto our important flag. The attack should be dead in the water, shouldn't it?
Well, not so fast. And here's that curveball I mentioned. Compilers these days are incredibly smart. Their main job is to make code run as fast as possible, and to do that, they perform all sorts of optimizations. And one of those optimizations might be, you guessed it, reordering your variables on the stack for efficiency. So even though you swapped them in your code, the compiler might just swap them right back behind the scenes, leaving you just as vulnerable as you were before. You can't always trust the memory layout to match your code.
And this is such a critical point. Even if you get lucky and protect this one specific variable, a buffer overflow is still one of the most dangerous bugs out there. Why? Because an attacker isn't limited to just that one flag. They could overwrite other critical data. Or, and this is the real nightmare scenario, they could overwrite something called the return address and completely hijack control of the program. That's the leap from a simple login bypass to taking over the entire machine.
So let's zoom out for a second. Why do we care so much about a nerdy, technical bug like this? What does it actually mean in the real world? Well, it all comes back to the absolute core principles of security.
A buffer overflow is a true triple threat. First, it shatters integrity. An attacker can change how the program behaves, just like we did to get access. Second, it can destroy confidentiality. These bugs can sometimes be used to leak sensitive data, like passwords or private keys. And third, it impacts availability. A simple, clumsy overflow can just crash the program entirely, making it unavailable to anyone. It hits every single pillar of information security. It's the whole package.
And that really brings us to the big takeaway here. The buffer overflow isn't some new exotic attack. It's one of the oldest, most famous vulnerabilities in the history of computer science. We've known about it for decades, and yet, here we are, still talking about it because it keeps showing up in modern software. So what does its stubborn persistence tell us about the software we all rely on every single day? It's a pretty stark reminder that even the tiniest, simplest looking flaws can have absolutely massive consequences.